in a fluid propagates in the form of wave, and we have discussed the properties of one dimensional wave motion. Now, if a body moves through a fluid which is at rest, then that body disturbs the fluid, and this disturbance in general is not small, and hence the disturbances in this fluid propagates or transmits to the other parts of the body and also to the other parts of the fluid through wave propagation. The wave motion is compatible with the motion of the body, and these wave motions that determines the pressure on the body as well as the complete flow field around the body. Now, usually when the flow is subsonic, the wave motion is usually not considered, it is not essential, it is not even convenient. However, when the flow is subsonic, supersonic, then this wave motion can be used to construct the flow in a much more convenient way. Particularly, if we consider a motion is steady, then we can study the motion from a reference system where the body is at rest and the fluid flows over it. Now, when the flow is supersonic, that is the relative wind is supersonic, the waves cannot propagate ahead of the immediate vicinity of the body, and as a result this wave system also travels with the body, and with respect to the reference system, this wave system appears to be stationary. That is the wave system that moves with the body. With respect to that reference system, the wave system appears to be stationary, and because of this limited upstream influence in case of a supersonic flow, where the waves cannot propagate ahead of the body, this principle, which is known as the limited upstream influence principle, allows the flow to be analyzed or constructed in a step by step manner. However, to consider flow about a body, we need one more tool. We have seen that in one dimensional flow there is a shock wave, and that shock wave is essentially normal. However, when the general motion is 2 or 3 dimensional, which is of course much more geometrical complex, this stationary shock wave, it can either be normal to the flow direction or can also be oblique to the flow direction, and we need to obtain the relationship between various parameters across an oblique shock. Now, these relations across an oblique shock can be obtained directly by considering the equation of motion in 2 dimension or in 3 dimension if necessary. However, they can also be obtained in a much simpler manner by transforming the normal shock relations to oblique shock relations. Let us consider an oblique shock, and the flow velocity, let us say this is an let us consider an oblique shock. And consider that the flow velocity ahead of this oblique shock is W 1. The flow velocity ahead of the oblique shock is say W1. Now, we can resolve this velocity into two components, where one is normal to a shock, and let us say this component is u1 and the other component is parallel to the shock. We call this to be v1. This angle, oblique shock angle with respect to the horizontal, we call this the wave angle beta. That is beta we call the wave angle, and what we can see that this wave angle beta is tan inverse u1 by v1. Mach number ahead of the flow Mach number ahead of the body, sorry, ahead of the shock, flow Mach number ahead of shock, where a1 is the speed of sound ahead of the shock. Now, since the normal component of upstream velocity, that is W1, normal component of is u1 and u1 equal to W1 sin beta, and hence u1 by a1, which we can call the Mach number based on the normal component. Mach number based on the normal component is m1 sin beta. Now, considering these two component of the flow velocity, we see the component v1 or the tangential component is parallel to the shock and it does not cross the shock and hence is not affected by the shock. However, the normal component u1 which crosses the shock undergoes a change as given by the shock relations, that is the normal shock relations, because this shock is normal to the flow velocity u1, and as you have seen earlier, across the shock the normal component of the velocity reduces. So, this u2 is smaller than u1 and will be given by normal shock relation. The component v1 does not change and remains same, that is v2 equal to v1, and the resultant velocity is w2. So, we see that through the oblique shock, this W2 which have a magnitude smaller than W1, that is W2 is also smaller than 1 W1, and not only that, the direction of W2 is different from the direction of W1, that is the flow when crosses an oblique shock or passes through an oblique shock, it changes its direction or it undergoes a rotation or turn. This angle theta, that is the angle between W1 and W2, is called the flow turning angle or deflection angle. Flow turning angle or deflection angle. And also you can see that W2 or the flow velocity after the shock turns towards the shock, and this is what is usually called the positive turn, that is where the flow is turning towards the shock, or as it here in this case the deflection is positive, that is flow deflection is positive when the flow turns towards flow deflection is positive when it turns towards the shock. Now, if we compare this situation with a normal shock situation, what we see here that with respect to this component of velocity u1, the flow velocity, it is the shock is basically a normal shock. So, we can treat this situation as if a uniform component has been superimposed with the flow. Now, a superposition of a uniform flow velocity is not going to affect the static pressure and other static parameters like density and temperature, and hence the relationship between static pressure, density and temperature ahead and behind the shock can be directly obtained from the normal shock. However, it must be remembered that the flow component that will come into picture is simply u1, or the corresponding Mach number that will come in the relation is mn, that is m1 sin beta, and hence we can get all the oblique shock relations particularly just by simply changing m1 to mn or m1 sin beta. Consequently, that is rho 2 by rho 1, T 2 by T 1, P 2 by P 1 can be obtained from normal shock relation by replacing with Mn or M1 sin beta. That is, we can now write rho 2 by rho 1 equal to gamma plus 1 M1 square will be changed to M1 square sin square beta M1 square sin square beta plus 2. You can see clearly that these are the same relationship as was derived in case of normal shock, only that upstream Mach number m 1 square is replaced by now upstream normal component of the Mach number m 1 sin beta. Similarly, pressure which is 1 plus 2 gamma by gamma plus 1 into that m 1 square again replaced by m 1 square sin square beta minus 1 . Similarly, the temperature ratio which is also equal to the square of the ratio of the speed of sound and also the ratio of the static enthalpies is again 1 plus 2 into gamma minus 1 by m 1 sin square beta . See that in all these relations for a normal shock, the parameter m 1 is now replaced by m 1 sin beta. The entropy change is again given by log of 1 plus 2 gamma by gamma plus 1 into m 1 square sin square beta minus 1 to the power 1 by gamma minus 1 into gamma plus 1 m 1 square sin square beta by gamma minus 1 into m 1 square sin square beta plus 2 to the power minus gamma by gamma minus 1, and this is also gives the stagnation pressure. And once again, as in case of a normal shock, since this process is adiabatic, the total temperature remains the same behind and ahead of the shock. Once again, we see that the ratios depend only on the normal component of the velocity or normal component of the Mach number, and of course, on the gas itself. And once again, that since S 2 must be greater than S 1, once again we find that this requires that m 1 sin beta must be greater than 1. Now, since S2 is greater than S1. This implies that M1 sin beta has to be greater than equal to 1. And of course, this sets a limit or a minimum value for the wave inclination for a given free stream Mach number m 1 or given upstream Mach number m 1, there is a minimum value of beta which is possible. The maximum is of course when beta is pi by 2 or when the shock is normal. So, this sets a minimum, sets a minimum beta for a given m, maximum beta is that is a normal shock. Hence, for a given upstream Mach number m 1, we have hence for given m 1, the beta lies within the range sin inverse 1 by m 1 less than beta less than equal to pi by 2. And for each wave angle beta, there is a corresponding deflection angle theta. Now, to find the Mach number downstream of the shock, we can obtain this by noting that m 2 equal to W 2 by A 2 and m 2 n is U 2 by A 2 and U 2 is simply that is m 2 sin beta minus theta, that is because U 2 equal to then once again writing the relationship between m 1 and m 2 for normal shock and replacing upstream Mach number m 1 by the normal component of m 1, that is m 1 sin beta, and the downstream Mach number m 2 by m 2 sin beta minus theta, we have m 2 square sin square beta minus theta is 1 plus gamma minus 1 by 2, m 1 is replaced by m 1 square sin square beta m 1 square sin square beta minus gamma minus 1 by 2. and this gives us all the necessary Rankine-Hugoniot relationship for oblique shock. Now, let us see that we also have tan beta equal to u 1 by v 1 and tan of beta minus theta is u 2 by v 2 and v 2 is of course v 1. So, this is u 2 by v 1 and consequently, we get tan beta minus theta by tan beta equal u 2 by u 1 or equal to rho 1 by rho 2, and this rho 1 by rho 2 we have already written as gamma gamma minus 1 m 1 square sin square beta plus 2 by gamma plus 1 m 1 square sin square beta. Now, using this trigonometric relationship tan beta minus theta by tan beta equal to gamma minus 1 m 1 square sin square beta plus 2 by gamma plus 1 m 1 square sin square beta, can be manipulated. The trigonometric relationship can be manipulated to show that tan theta equal to 2 cot beta m 1 square sin square beta by m 1 square into gamma plus cos 2 beta plus 2, which is a very well known and very widely used relationship and usually known as theta beta m relations. This is called the theta beta m relation. It expresses the flow deflection angle in terms of the wave angle and upstream Mach number, and of course, the gas property specific heat ratio. However, we see that here theta can be explicitly determined if m 1 and beta are known. However, if m 1 and theta are known, beta can only be solved from this implicit relationship. We also see that theta equal to 0. This shows that when theta equal to 0, when beta equal to sin inverse 1 by m 1 or and pi by 2. That is at the lower limit of beta and the upper limit of beta. In both cases, the flow deflection is 0. That of course, we have seen for normal shock, there is no deflection in the flow retains its earlier direction, and also we see that when beta is the lowest value, that is sin inverse 1 by m 1, then also there is no deflection in the flow. Now, this theta beta m relation also shows that within this range of beta, that is beta lying between sin inverse 1 by m 1 and pi by 2, the theta is positive, and since theta is 0 at both at the lowest value as well as the highest value of beta. So, obviously, that theta must have a maximum within this range of beta. That is, for each value of m 1 there is a maximum value of possible theta, and if also it shows that if theta is less than theta max, then for each value of theta and m there will be two corresponding value of beta or two corresponding solutions. Now, out of these two solutions, the larger value of beta gives a strong shock, and for the lower value of beta the solution is called the weak shock, and usually for a strong shock the downstream flow is subsonic. However, for a weak shock the flow is usually supersonic downstream. However, there is a very small range of value of theta which is slightly smaller than theta max. Even for a weak shock solution, the downstream Mach number can be subsonic. We can plot this m theta beta relationship as say in degrees and theta is also let us say in degrees. Let us say this is the 90 degree corresponding to the normal shock. For different values of m 1 we will have different curve. If we consider upstream Mach number to be infinite, thing like this, this is for m 1 equal to infinity, where the lower limit is 0. For all other values there will be this is the increasing direction for you see as the value of m 1 decreases, the value of the lower limit of beta, that is sin inverse 1 by m 1 increases. Now, if we join all the theta max values for each of these Mach number, let us say that this is what is the sorry. This is a theta equal to theta max line, and this is the line for M2 equal to 1, sorry. Now, if we look to this curve, you can see that higher curve for higher Mach numbers envelops the curve for the lower Mach number. If we have the solution corresponding to a value for which beta is higher of the two, then that solution is called a strong shock solution, that is to the right of the line corresponding to theta equal to theta max. Similarly, this is the line corresponding to downstream Mach number 1, that is for all these part of the values the downstream Mach number will be less than 1, and for all values to this side the downstream Mach number will be more than 1, that is the downstream flow will remain supersonic if the solution corresponds to any point within this part of the curves. Similarly, for this part of the solutions the downstream Mach number is subsonic. So, what we see that for all strong shocks downstream Mach number is less than 1, but for weak shock, for only those values where theta is slightly less than theta max, the weak shock can also have downstream flow as subsonic. So, this is a very useful relationship, and the curves are also very useful, theta beta m curves, so theta beta m relations. Now, going back to the theta beta relation in this form, that is tan beta minus theta by tan beta equal to gamma minus 1 m1 square sin square beta plus 2 by gamma plus 1 into m1 square sin square beta this relation can be expressed also in the form, it can also be expressed in the form 1 by m1 square sin square beta gamma plus 1 by 2 tan beta minus theta by tan beta minus gamma minus 1 by 2. And this can also be written as m1 square sin square beta minus 1 equal to gamma plus 1 by 2 m1 square sin beta sin theta by cos beta minus theta. We should also note that the term m1 square sin square beta minus 1 takes the role of m1 square minus 1 in the normal shock relation and can also be called as the strength of the oblique shock, as m1 square minus 1 is the strength of the normal shock. Similarly, the m1 square sin square beta minus 1 can be taken as the strength of the oblique shock. So, this is the way that oblique shock strength we can express. Now, we can make a approximation that for small values of theta, we have for small flow deflection that is theta is small, we can approximate this relation m1 square sin square beta minus 1 is approximately gamma plus 1 by 2 m1 square tan beta into theta. That is, for small deflection angle, the oblique shock strength is proportional to the flow deflection angle. Of course, the flow deflection angle is expressed in radian. So, these are the basic relationship that are required for oblique shocks, and with knowing about this oblique shock, we will now first try to construct our first example of supersonic flow, that is supersonic flow over a wedge. Now, for this we will use the basic concept of inviscid flow, that is any streamline and inviscid flow can be replaced by a solid boundary. And incidentally and immediately we see that then the oblique shock provides the solution of a supersonic flow or inviscid supersonic flow in a corner. Let us say, that is, if we have a corner flow in a corner, let us say that this is what we have a tree and this is the corner. So, we know that the inviscid flow boundary condition enforces that the flow must be parallel to the solid wall. The flow must be parallel to the solid wall. So, if a flow which is parallel to this, that is, if this is a straight line of the flow, then here also it must be parallel to the body or parallel to the solid wall. So, these are the streamlines These are the streamlines. So, a corner of angle theta turns the flow by an angle theta, and what we have seen that earlier, that is what exactly an oblique shock does, that it turns a flow by an angle theta for a given supersonic stream of Mach number m 1 will be turned by angle theta, provided there is a oblique shock provided there is an oblique shock. So, this is the oblique shock of given angle beta. So, once we know this m 1 and theta, from the theta beta m relations or theta beta m curves, we can find out what is the wave angle beta. However, now we should note once again that the theta beta m relation, though gives theta explicitly when m 1 and beta, when m and beta are given, however, it does not give beta explicitly, rather beta needs to be solved implicitly. And a question of course comes that out of the two solutions, which solution should be taken. That is also simple. If theta is less than the theta max, we should take the lower value of beta, that is the weak shock solutions, and to be precise, that nature usually prefers the weak shock solution. Now, this can easily be used to obtain the flow over a wedge. So, if we have a symmetric wedge, so if we consider flow over a symmetric wedge, let us say flow over a wedge, of course, only supersonic flow. So, if the wedge is symmetric, let us say that both are theta, and the flow will be obtained by two oblique shock of angle beta. Now, the flow on each side of the wedge is determined only by the inclination of the surface on that side. So, it is not essential that the wedge have to be symmetric. If these two angles are different, that is theta 1 and theta 2 are different, the two angles will be different. However, this part of the flow will be simply governed by this inclination, and this side of the flow will be simply governed by this inclination, and a parallel streamline here will remain parallel again. For the time being, we will not consider about this corner and what will happen in that corner. Later on we may discuss about the turning at this corner, but for the time being we will consider that these waves are infinite. So, that a parallel stream simply turns by this wedge angle or wedge half angle and remains parallel to the wedge surface. Now, we will come to one more situation. Let us say that the flow downstream remains supersonic. The wave angle beta decreases with decrease in the wedge angle theta. The wave angle beta decreases with decrease in the wedge angle theta. Now, when theta decreases to 0, that beta decreases to the limiting value mu. Say, so we will consider what are called as Mach lines. When theta approaches 0, beta approaches to mu equal to sin inverse 1 by m1. Of course, assuming m2 still remains greater than 1. Now, in this situation, shock strength m1 square sin square beta minus 1 is 0, and so are all the jump relations. All the jumps are 0. That is P 2 by P 1, rho 2 by rho 1, T 2 by T 1, they are all equal to 1. That is, in this situation practically there is no discontinuity anywhere, the flow is continuous, and we can say that then there is nothing unique about this particular oblique shock. That is the limiting condition of oblique shock. No discontinuity is created, there are no jump in any of the flow quantities, and the flow is continuous. And hence, there is nothing unique about the point where this wave originates. We can take it any point in the flow, and this angle mu then becomes simply a characteristic angle associated with upstream Mach number m1, and this m1 is called, this mu is called the Mach angle. Mu is called Mach angle, or the oblique, and the oblique shock in this case becomes such oblique shocks are now called Mach lines or characteristics lines. Mach waves, and they are nothing but the characteristic lines. and considering any point on any particular streamline, we can have a Mach line to this line as well as to this side, and these are then called left running Mach lines. Now, of course, if the flow is non-uniform, then the Mach number changes throughout the flow and consequently, the Mach angle mu also changes and these Mach lines become carved. So, at any point in a two dimensional flow, there are always two lines which intersect a streamline at the angle mu. Similarly, in 3D flow, the Mach lines or the characteristics, they define a conical surface with the vertex at P. So, in a two dimensional supersonic flow is always associated with two families of Mach lines, they are denoted by these 11 plus or minus. The plus set runs to the right of the streamlines and called the right running characteristics, and the minus set runs to the left of the streamline and called the left running characteristics. And these are analogous to the characteristics that we have discussed earlier in our discussion in one dimensional waves. They are same characteristics line as in the xt plane. Like those characteristics in the xt plane, these Mach lines also have distinguished direction, that is the direction of the flow or the direction of increasing time, and this is related to the fact that there is no upstream influence in supersonic flow. So, to summarize, we have obtained the oblique shock relations from the normal shock relations themselves, just by replacing the normal component of Mach number in place of Mach number, that is m 1 is replaced by m 1 sin beta and m 2 is replaced by m 2 sin beta minus theta, or beta is the wave angle and theta is the flow deflection angle. We have seen that in an oblique shock, the wave angle is subjected to a fixed range with the minimum value being sin inverse 1 by m 1, the maximum value is of course, the normal shock angle pi by 2. We have also seen the possibilities of weak solution and strong solutions, and also have seen that there is a maximum deflection possible for a given Mach number, and we have also seen that when the wave angle becomes sin inverse 1 by m 1, then the shock is practically of 0 strength and there is no jump across this shock, and these oblique shocks are then called simply the Mach waves or the characteristics, which are analogous to the characteristics in one dimensional wave motion in xt plane.